Hello, and welcome to our next set of college algebra notes. We're on Unit 2, Outcome 4 for today. So in this section, we actually are going to mostly just solve several different types of equations. We're going to start off solving rational equations, and then we're going to do the second half is going to be solving radical equations. So both of these are probably something you've seen before. If you took Math 101, Intermediate Algebra, before you took this class, or maybe in your high school algebra class. So I'm not going to get super deep into either of these. If you need more practice with these, which some people do, you might want to check out some related Khan Academy videos. I've got links in the MyLab course. They might help you with these sections. But yeah, so we're going to get started. We're going to start with rational equations. To be a rational equation just means that you're an equation that has x's, or the variable, in the bottom of a fraction. So it's rational, meaning rational is kind of the term for fractions, and these expressions are special just because they have x's in the bottom of fractions. Now there's kind of one technique that you can use that can work for any of these, and so I'm going to show you that technique, because 9 times out of 10 that's just what I use to deal with these equations, and that's to multiply everything by the least common denominator. When you think of the least common denominator, you're thinking of something that you can take any of the denominators and multiply to get. So like in this first equation here, we have an x in the denominator and we have a 3x in the denominator. So the least common denominator, the smallest thing that I could get from either of these by multiplying, would be 3x. 3x times 1 is still 3x. And x, I can just multiply by 3 and get 3x. So the trick here for these is to multiply by the LCD, the least common denominator. So here, since 3x is the LCD, that's the common denominator, I'm going to multiply this whole expression. I'm just going to do big parentheses and say everything in here times 3x. That's how I'm going to do this. I'm going to take 3x, I'm going to multiply the first part. So I'm going to take 3x times this, 5 over x. Now if you multiply this right now, since this is a fraction and this is like a whole number, remember that you can always put a 1 on the bottom of the whole number, and so you end up multiplying 3x times 5, because you always multiply tops of fractions. You multiply 1 times x. Now, the 1 times x will, you just get x, right? So I'm not really going to worry about the 1 on the bottom, because when you multiply by 1, it doesn't change things. So I really just going to multiply the top number, 3x, times the top. And I'll just keep the bottom. But if I do that, if I do 5 times 3x, 5 times 3 will give me 15, and I have an x. And I have an x on top and an x on bottom. And what I notice is that the x on top and x on bottom would end up canceling. So instead of multiplying and then canceling, I'm actually going to do a little trick here where I cancel as I go. So every time I multiply, I'm going to think about what's on the bottom and say that part of the common denominator is going to cancel out that time. So the x's would cancel, and I'm just going to multiply the top by the 3. So basically doing the canceling first before I do my multiplication. That way I don't have to worry about canceling when there's lots of stuff. When the numbers are already kind of separate and smaller, maybe it makes the canceling a little bit easier. I'm going to cancel these x's first. I'm just going to multiply 5 times 3. So I'm going to do 5 times 3 for the first part. Then I take the whole 3x. It's not canceled forever. Some people try and do this and they'll cancel the x here and think that everything else multiplies by 3. No, this is 3x's times all 3 parts. I'm just saying that over here, once I multiply, the x's would cancel. Now I'm going to take this whole 3x again, and I'm going to multiply it to this part. Even though there's no bottom on the 4, we're still multiplying everything here times 3x. We multiply the 4 by 3x as well. Now the bottom here, there isn't a number on bottom, so there's nothing to cancel. So I'm just going to multiply the 3x times the 4. Don't forget the minus here, and 4 times 3 is 12. And now we actually have the x because we did the 4 times the whole thing. Last step, I'm going to do the 3x times this 10 over 3x. Don't forget your equals when you're writing this. And notice that the 3x and the 3x, those whole things are going to cancel, right? There's a whole 3x on the bottom, there's a whole 3x on the top. So that's completely going to cancel. There's nothing left. So on the top, I'm just going to write down the 10. I should have just gone ahead and multiplied 5 times 3. That was 15. Could save myself a step there. But there we go. So we got 15 minus 12x equals 10. And so that's what I did by multiplying 3x through. Since it was the common denominator, it got rid of all the fractions. So you can take almost any rational equation like this and multiply by a common denominator that's got all these parts in it. Multiply by that, and it will cancel all the fractions. So you just get an equation without fractions anymore. And then you could just solve just a regular equation, one without fractions. So like here, I'm going to solve just by subtracting 15 across. You subtract both sides, so get rid of this one. So negative 12x equals negative 25. And then I'm going to divide both sides by negative 12 to get rid of this negative 12 because I do multiplication with division. And so we just get x equals negative 25 twelfths. Oh, sorry, negative or negative makes a positive. Positive 25 twelfths is what I meant to say. Okay, so that's the idea. So we can multiply by a common denominator, get rid of the fractions, and then just solve an equation that's left. Just a regular equation. The big trick is just to figure out what the LCD is in the first place and multiply that by that so that you can get rid of these common denominators. Now, this is probably my go-to method. 9 times out of 10, like I said, I use this method. There is one specific case where I use a different method. I'm going to show you the other method next. And that specific case is when you have what this looks like right here. This is called a proportion. So a proportion is just a fancy name when you have a fraction equals a fraction. So it's just going to be one fraction on each side. Up here, this wouldn't be a proportion because we have a fraction and a number. These are separate. So it's not a proportion right now. You could like rewrite some of this stuff to make a proportion, but I think that's more work. So this one I'm going to solve that way. But I have this where it's already a proportion, where it's fraction equals a fraction. Instead of doing the LCD trick, multiplying everything over by the LCD, in this case, when you have a proportion, you can do cross multiplication. So cross multiplication is when you say, if these two fractions are equal, then their cross products have to be equal. So if this fraction equals this fraction, then the diagonal multiplication here and the diagonal multiplication there have to give you the same value. If that doesn't work, then they're not actually going to become equal fractions. So we're going to do cross multiplication. So I'm going to take 4 times x minus 2, 4 times x minus 2, and say that has to be equal to 3 times x plus 3, 3 times x plus 3. Those two products have to be equal. So if these two fractions are equal, these two cross products have to be equal. And so that's something you can do with any proportion like this, where you have two fractions just set equal to each other. You can cross multiply them and say that those products, those cross multiplications have to be equal. So now you can solve this equation instead of our original equation, because now this equation doesn't have any fractions in it. So those are the two main tricks or techniques I use, the multiply by LCD method, and in this case, the proportion or cross multiplication method. So here, I'm going to go ahead and solve this. I want to get rid of the parentheses. I'm going to distribute both of these. So here I get 4x minus 8. Here I get 3x plus 9. Now I'm going to simplify. I'm going to get all the x's on the same side, so I'll subtract 3x across, which means I need to, so I'm getting rid of this, which means now I need to move the 8 over to this side because I want just x's on this side. So I'll add 8 to both sides. This one. So 4x minus 3x just gives me x. There's only one of them. Equals 9 plus 8 gives me 17. So after doing the work, I find that x is 17. So those are the two main methods, right? So the two main methods are the multiply by the LCD trick method and then the cross multiplication method. Again, cross multiplication though is only good in one case, and that's with the proportion. As soon as you don't have a proportion, you can't use this cross multiply. When you have more than two things, you can't just multiply diagonals because it doesn't work when there's 3 parts or 4 parts or whatever. Now, both of these actually have one more thing we have to worry about, and I haven't mentioned yet, which is what I call restrictions. When you're solving equations like this, and you have x on the bottom of a fraction, you do have to worry about the possibility that if you solve this, the number you get might be the same number that makes you divide by 0 in this expression, this equation, because it has x's in the bottom. There are some values that you're not allowed to use, some values that make you divide by 0. So when you're doing these problems, you should always stop and check, am I going to make myself divide by 0 if I use that number for x? So what I do is I check the restrictions. I check what I'm not allowed to use. I call these restrictions because these are the numbers that won't work because they make you divide by 0. So for this case, x can't be, well, if I put 0 in the bottom here, that's 5 divided by 0. So x can't be 0 because that would be like having a 0, 5 over 0. Same thing here, actually, because when I do 3 times x, the only way that's going to be 0 is if x is 0. Every once in a while I have someone tell me, what about -3? Well, 3 times -3 would be -9. Since this is multiplication, the only number we really have to worry about is 0. So in this one, the only restriction, the only number that's not allowed to work is 0. Since 25 over 12 isn't 0, we're fine. This number works. But there's a possibility that when you do this, the answer you get could match your restriction. And if they match, you have to toss that answer. You're not allowed to use any answer that's one of your restrictions. They're restricted from use because if you try and use them, you divide by 0. Let's try the next one. Here, what would make this one be 0? So if I check my restrictions, the numbers I'm not allowed to use. Again, I'm going to think about what x can't be. Well, now 0 in this case actually isn't a problem, right? Because 0 plus 3 is 3, that's fine. 0 minus 2 is -2, that's fine. The only number we can't divide by is 0. So what I actually want to avoid this time are -3, because -3 plus 3 would be 0, and that would be a problem down here. And +2, because 2 minus 2 is 0, and that would be a problem here. So the actual restrictions this time are -3 and 2. Those are the things I want to avoid. So you'll notice here, restrictions can be all kinds of numbers. It really depends on what expression you have at the bottom of your fractions. And yes, you can have more than one restriction, right? So you do want to check and make sure you find all the restrictions. Once you know the restrictions, then you can check and see, did the number I get match those restrictions? If it does, you toss it. If not, like 17, you keep it because it's good. 17 is not -3 or 2, so we're allowed to use 17. 17 is a valid answer. There's always a possibility when you're solving these rational equations, because x is on the bottom, there's always a possibility that the answer you get would make the bottom 0, and if it does, then you can't use it, so you have to toss it out. Okay, let's try a couple more of these, but that's the main idea for this first half, is using, multiplying by the LCD or the proportion. And like I said, most of the time we'll do the LCD method, so that's what we'll do probably the rest of these problems. So like here, I have 3 parts, so I can't use proportions because I'd have to just have a fraction equals fraction. If you took out this -3 part, then it would be a proportion. If you had something like that, then you could use the cross multiply. But since there's 3 parts here, we have to use the other method, which is to multiply by the LCD. I know some people have done this in previous classes where they just made all expressions have the same denominator, and that works fine. You can do that method as well. I have nothing against that. I just think my method's a little bit easier. That's why I just do this method. A lot of these problems have more than one method. Okay, so I'm going to take this and multiply the LCD. In this case, the LCD is x plus 2 because both of these have the same denominator. So you can have something like this where it's an addition or subtraction. Could be your LCD. Because that's all one number. We just don't know what x is. So if you think about this is just a number. X times plus 2 is going to give you some value. If x is 10, this would be 12. But we don't know what x is. So this is just one number. So this is your LCD. It's the number on the bottom. And we can multiply everything here by that LCD. So we're going to multiply by x plus 2. Just like before, we're going to multiply it to each part. So I'm going to start with the first part. I'm going to notice that there's an x plus 2 on the bottom. And there's an x plus 2 over here. These x plus 2's match. They cancel. They're opposites. So instead of multiplying by x plus 2 and then canceling, I'm just going to go ahead and cancel now and just say I've got 10 here. I go to the next step and I've got the 3 that doesn't have a denominator. There's no bottom here. So nothing cancels. Here I'm actually going to have to multiply the 3 times the entire x plus 2, the whole amount. Next one, I go to the 5x over x plus 2. This time I do have an x plus 2 on the bottom, and that will cancel the x plus 2. So I'm just going to leave the 5x by itself. So I have minus, don't forget the minus sign, and the 5x. So here, because all the denominators matched, I made it pretty easy because you just had one denominator, and it canceled both of those. Okay, now I got a regular equation, no fractions to deal with, and I can just solve it like I normally would. I would get rid of the parentheses by distributing. I'm going to distribute like that. So 3x plus 6 minus 5x equals 10. I'm going to combine, I get 3x minus 5x. 3x minus 5x gives me a negative 2x. I subtract 6 from both sides just to get this side so it's just x's. So I got rid of the 6 over here. So I get 10 minus 6 is 4. So I get 4 equals negative 2x. I'm going to undo multiplication by dividing. I'm going to divide both sides by negative 2 because the opposite of multiplication is division. So I divide by the same number. That way they cancel. Multiplication, division, cancel. And 4 divided by negative 2 is negative 2. So I get that x is negative 2. Now this is the problem where you get to the homework, you put that in, it counts it wrong. And you go, wait, I did the problem all right. This is great. Why did I get it wrong? And this is where the restrictions really matter. because if you don't check your restrictions, you're going to get this one wrong. This can happen in the homework, it can happen on the quizzes, it can happen on the test. So always want to check those restrictions so you don't mess up the problem, especially on the test. So the restrictions in this case is x cannot be -2, right? Because -2 plus 2 would be 0. So x can't be -2. It could be anything else, but it can't be -2. So that's why this number is not allowed. There's no valid solution here because the only one we found that works, we solved this, and we found one that we thought works, we're not allowed to use. Because if you put -2 in here, then you really divide by 0. And you can't divide by 0. It doesn't give you a value. It doesn't really work. If you try to pretend like you can or whatever, it just blows math up. It just makes math not work anymore. You cannot divide by 0. So we're not allowed to divide but use -2 for x, so we can't use -2. So the value we found doesn't work. So in this case, we say there are no solutions. The only solution we thought worked when we solved it is one we're not allowed to use. So you always got to check restrictions, and this can happen, right? Where you solve a problem, you think you found an answer, but you didn't check restrictions and you get it wrong. So you want to make sure you check those restrictions. Okay, let's try one more. This was probably the most complicated one you'll see, mostly because before we can even begin, we got to figure out what the LCD is. It's a little trickier here because it's got 3 different things going on. So we're going to have to actually look at all 3 parts to figure out the LCD. But before we can really figure out the LCD, the thing you do with these expressions like this is you always want to factor it when you're looking for the LCD. Now the first 2 they're fine. They're just one part, so there's nothing you can do there. But this last one, being a trinomial like this, it will factor. So we're going to factor this first, because that'll help us figure out what the LCD is. Right now, it looks like there's a whole bunch to put in there, but if we factor this, we'll actually figure out it's not as bad as it looks. So I'm going to factor this. So to factor this, I think about what multiplies for -6 and adds for 1. Remember, that's how you factor these trinomials. Since it's an x squared at the beginning, I put x is here. So, okay, 1 multiplies for -6, adds for +1. I know 2 times 3 gives me 6, so 2 and 3 sound good. One of them would have to be negative, so they multiply for -6. But I want the bigger one to be positive, so that when I add them, I get a +1. So I'm going to do a -2 and a +3. So that's how I figure out how to factor it. So I say, oh yeah, 3 times 2 is 6. If it's a -2, I'll get a -6. And if I add these, I get a +1. Now that I factor that, you can see that there's actually not as many parts as we thought there were on the bottom. There's 3 parts, but these 2 are repeats, right? They're the same as the bottoms we already saw, right? So we have the x minus 2 here and the x plus 3 there. So the LCD that we're going to multiply by, so this LCD is actually just going to be both parts. It's going to be x plus 3 and x plus 2. Remember, this has to be something you can multiply to get. Well, this is the same, so you can multiply by 1 and get that. Order of multiplication doesn't matter. So it doesn't matter that I switch the parentheses around because it's still both parts. Here, x minus 2, I could just multiply by x plus 3 and get this. Here, x plus 3, I can multiply by x minus 2 and get this. So this is the common denominator because it has all the parts. So that's one trick, because if you have everything written as multiplication like this, it's a lot easier to figure out what your LCD has to have in it. It's got to have all the parts, basically, so that you could take any one of these and multiply to get that. So this is your LCD. That's what we're going to multiply. So we're going to take this whole thing times the LCD. So we're going to multiply times both x minus 2 and x plus 3. Both parts, right? Both of those parts. When we go to the first part, we take this one to the first part. Here, the x plus 3 parts are canceling because there's one here and there's one there. So if I multiply and put this on top, we'd have the x plus 3 on top, x plus 3 on the bottom, and they would just cancel. So we're going to take them out right now. I'm just going to leave the x minus 6 because the x plus 3's cancel. So we're going to leave the x minus 6, sorry, I said x minus 6, I meant x minus 2. We're going to get rid of the x plus 3's, but we're going to leave the x minus 2 and the 6. So we get 6 times x minus 2 because the x plus 3's are going to end up canceling. Next part, I have I have 5, and then I have an x minus 2 on the bottom. Well, now the x minus 2's are going to end up canceling. So I'm just going to multiply with the x plus 3 because the x minus 2's cancel. So I'm going to do 5 times x plus 3. And then my equals. Next part, I take this one times this one. Here, it has both the x minus 2 and the x plus 3. So both parts are going to cancel. If I put this on top, I'd have both of the x minus 2 on top bottom, x plus 3 top bottom, they'd cancel, so you'd just be left with the minus 21. So that's how I write that. So again, each time I do this, I'm thinking about when I multiply, what would end up canceling? Because I can just get rid of that right now instead of writing it down and then canceling it. Okay, so now I have this. Now I can go ahead and solve it because now it's just a regular equation, no fractions in there. So I can distribute to get rid of parentheses. We've been doing a lot of that. Here, 6 times x is 6x. 6 times 2 is minus 12. Don't forget the minus. Here I have a minus 5. When you distribute here, make sure you distribute the negative with the 5. Make sure you get this right. A lot of people will do like negative 5x, but then they'll have like plus 15 when they do 5 times 3. It should be a minus 5x, and then minus 5 times 3 should give you a minus 15. A lot of people get this sign wrong when they're not careful. Okay, and then negative 21 there. Next thing I want to combine, I got 6x and negative 5x, so let's combine for x. Right, 6 minus 5 is 1, so just 1x is an x. Negative 12 minus 15 more gives you a negative 27. So again, when you combine negatives like that, this is negative plus another negative here, I end up with negative 27 equals negative 21. Last thing, I want to get rid of this minus 27, so I'm going to add 27 to both sides. So I get x equals, what was that, 6? Yeah, x equals 6. So I got 6 for my answer. Not done quite yet though, because remember, every time we do a problem like this, we have to go back and check restrictions. So we check restrictions. So check restrictions. Again, I'm thinking about what would make the bottom 0. With these problems, when there's lots of bottoms, one thing that's nice is you can actually find all the restrictions in the LCD. So whenever you're looking for restrictions, you don't have to look everywhere for them. You could just look at the LCD, because the LCD will have all the restrictions. So I notice here that, x plus 3, that would be 0 if x is negative 3. So I don't want x to be negative 3. That's one of the restrictions. X minus 2, that one's going to be 0 if x is 2. The other restriction would be x is 2. So you'll notice over here, here you can see there's the negative 3 restriction, there's the 2 restriction. This one, when it factors, you can see it has both the 2 and the negative 3. But all of those, like I said, show up in the LCD. So if you found the LCD, that you found all the restrictions. You just look at that and see what makes that 0. Whatever makes the LCD 0, those are going to be restrictions, because those are all in the bottom. Okay, so I can't use negative 3, can't use 2, but my answer is 6. So we're good. We're happy. As long as it's not negative 3 or 2, you can keep it. But if you had negative 3 or 2, you'd toss the answer out. Okay, I think I do have one more of these. One more. Okay, this one, I guess, is a little harder. I forgot. I think this one I grabbed out of the homework, so that's why I wanted to show it to you, because it was a little tougher. So this one, again, has 3 parts. So again, we're going to use the multiplied LCD. So like I said, you use that most of the time. The proportion trick is only in certain cases. Here again, we got to think about the LCD. Before I can think about the LCD, we do need to factor first, because you always factor so you can kind of see the parts of the LCD. Thankfully, the first 2 fractions are already factored. There's nothing I can do to break down x minus 5 or x, so we're just going to leave those as they are. So 10 over x minus 5 minus 2 over x. But we can break down this last term. Now the top, we can't factor that. That stays as this, so 13x plus 5. There's nothing to do with factoring that. But the bottom, where it has x squared minus 25, that's what we call a difference of squares. It's got a special factoring technique. A difference of squares like this factors into 2 parentheses, where the numbers and the parts match, but the signs are different. So one's a plus and one's a minus. That's how these always factor. The first part of each one is going to be the square root of the first part. So the square root of x squared is just x. So that's going to be the first part. The last part is going to be the square root of the last part. So square root of 25 is going to be 5. So if I take x plus 5 times x minus 5, it would give me x squared minus 25. And this difference of squares always factors to look like this, where the 2 numbers are these guys square rooted. Square root of x squared is x, square root of 25 is 5, and one's plus, one's minus. That's how those factor. Okay, now that I got all the parts, now I can think about the LCD. So what's the LCD? We want to multiply by that LCD, so we have to figure out what it is. So what's the LCD? Well, we need to have all the parts. So we need to have an x minus 5, right? That's one of the parts. We need to have an x plus 5, that's a part. I don't need 2 x minus 5s, because you can see that that one's there and that one's there. But I do need a plain x. Now you might say, well, don't I already have x's? Well, x is a different value than x minus 5, right? Because x minus 5 is going to be 5 less than x. X is a different value than x plus 5. That's a different number. So we do need an x by itself, because that's a different value. These are 3 different numbers, right? We have this number, which is 5 less than x, this number, which is 5 more than x, and this number, which is x. Those are all three different numbers, so they all need to be part of our LCD, our common denominator. So that is what I'm going to multiply everything here by. I'll multiply by x minus 5, x plus 5, and x, all those parts. And again, I'm going to do this to all three parts, and as I go, I'm going to cancel. So this first part, I'm going to look at that and say, oh, there's the x minus 5. That part's going to cancel. So the 10 on top is going to be multiplied by the other parts. When we multiply it by the x, I'm going to put the x in front. I don't know why I put it on the right side. I'll put it in the front. And the x plus 5. So multiplying by both parts, but the x minus 5 part, that was just going to cancel, so I don't need to multiply by it, because I can say, well, this part's going to cancel that part out, so just multiply what's left. Then I do the middle term. So I get this minus 2. The x part is now what cancels, right? The x part here cancels. So the 2, I'm just going to multiply by x minus 5 and x plus 5. So the 2 multiplied by the other two parts, but the x part of it would cancel. Last one, so take this expression times this last part. Don't forget your equals. Here, the 13x plus 5, so that 13x plus 5 is going to multiply by just the x, because both the x plus 5 and the x minus 5, both of those pieces are going to cancel. So we're going to just multiply this times x. And I do want to make sure the x goes to both parts. That's why I put parentheses here. Okay, so you can hopefully see how here I multiplied by just x, because both parts canceled. Here I multiplied by the other two parts, because just the x canceled. And here I multiplied by x and x plus 5, because just the x minus 5 canceled. Now I got to go ahead and multiply this out. So there's a lot of foiling and factoring and distributing to do here. So I'm going to distribute. Here I'm going to have to actually FOIL. So I got a lot of multiplication to do. So first off, I do 10x times x is 10x squared. 10x times 5 is 5. The 50x. Over here, I've got 13x times x is 13x squared. 5 times x is 5x. Over here, I'm going to keep the minus 2. I'm going to keep a big parentheses here. I'm going to go ahead and FOIL those two things out. So if I do FOIL this, x minus 5 times x plus 5, I can do x times x, get x squared, x times 5, get 5x, x times negative 5, get negative 5x, and then negative 5 times 5, get negative 25. But if you really pay attention, you should notice that this thing we have right here is actually just how we factored out this expression, right? It matches. So we already know what we're going to get. If we multiply those back together, we should get x squared minus 25. And you do if we did what we just did, because the negative 5x and the positive 5x would cancel. You'd just be left with the x squared part and the minus 25 part. So just something to think about. You know, there we kind of already knew how it should multiply because we talked about that earlier. Okay. Excuse me, sorry. Okay, so this next part, I still have a parentheses here I want to get rid of, so I'm going to go ahead and distribute this negative 2 through. So that's just one more step to get rid of all these parentheses. Negative 2 times x squared is negative 2x squared. Negative 2 times negative 25 is positive 50. 25 is 50. Okay, getting there. We got 10x squared over here still 50x over here. Okay, now that we got that all got rid of all those parentheses, we want to get all the stuff on the same side, because whenever you're solving a quadratic with an x squared, you want everything on the same side. So I'm going to subtract 13x squared from both sides. Subtract 13x squared. And I'm going to subtract 5x from both sides. 5x. Get rid of this thing. So you get negative 3x squared plus 45x minus 2x squared plus 50 equals 0. I do have some x squareds I can combine, so we're going to combine this negative 2x squared and this negative 3x squared. So negative 5x squared plus 45x plus 50 equals 0. Now this one looks really bad because I got that negative 5 in front and it looks like, oh, do I have to use like a formula on this? Well, there's actually a trick here you can do. So the trick here is to get rid of this negative 5, because notice that all these numbers divide by 5. Even 0 divides by 5, because when you divide 0 by anything, you get 0. So I'm actually going to divide by negative 5, because that will get rid of all these 5s. It will get especially this 5 in the front and give me something easier to factor. So I'm going to do that here. I wouldn't give you one like this on the test. This one I think is a little more difficult than we do on the exam, because there's so many steps to it. I just want to show you to help you out with the homework. But if you do get a problem like this, you could use the formula, and the formula will work and give you an answer. Here, I'm just going to show you a trick how you can kind of get an easier answer by factoring. Any problem I give you with rational expressions like this, if it does have a quadratic, I will make it so it factors. I'm not going to give you one where you have to use the formula. Okay, so negative 5 we're going to divide by on both sides. Here negative 5 is 1, so that just becomes x squared. 45 divided by 5 is 9, and a positive divided by negative is a negative, negative 9x. And 50 divided by 5 is 10, and then positive divided by negative is a negative. So, and 0 divided by anything is 0. So now that one's a little bit easier to factor. So just got to think about 1 multiplies for 10 and adds for 9. Well, 1 and 10 multiply for 10, and if you add them up with 1 being negative, you can get a negative 9. So it's got to be x of 1, x of 10. And since we have a negative 9, we want the bigger number to be negative, so it's going to be a negative 10 and a positive 1. So that's how we get 0. Now I take these both, and I set them both equal 0. X plus 1 equals 0, x minus 10 equals 0. Subtract 1 across, you get x equals negative 1. Add 10 across, you get x equals 10. So those would be my two answers, but I still have to check restrictions, right? Don't forget to check your restrictions. So last step here, you gotta check restrictions. So in this case, x can't be what? Well, again, remember you can look at the LCD. So here you can see 5 would be a problem. Negative 5 would be a problem. And since this x is by itself, the only way this is going to be 0 is if x itself is 0. If there's no addition or subtraction, it's always going to be that letter by itself. You're going to make that 0. So x by itself would be 0. That's like right here. If you have 2 over 0, you'd have problems. So that's why x by itself can't be 0. So my restrictions, x can't be 5, it can't be negative 5, and it can't be 0. Well, we got negative 1 and 10, which are not 5, negative 5, or 0, so these are both valid answers. And it's okay, you can have 2 valid answers. There are some equations where one might work, one might not, or they both might fail. You have to always check for those restrictions, because they never know when they're going to pop up. Okay, that's really the first half of this homework. And like I said, this one's probably going to show up in the homework. I would not put this on the test. If I could put something on the test, it'd probably be more like this one we just did, where there is some work to it, but it's not quite as extensive. You still do need to figure out how to factor and take those, factor them. And you also need to know how to multiply by the LCD. This I think is a much better show your work problem than like the next one we did, which I think was just a little bit too much. So I probably wouldn't put something on some exam. It might show up in the homework of the quizzes, but don't be too worried about like a problem like this on the exam. Okay, the second half of what we're doing is dealing with what we call radical equations. A radical means just something like this, a root. It could be a square root, cube root, fourth root. We're going to stick with just square roots and cube roots, or second and third roots for this section. We're not going to really worry about too much of the higher roots, but we'll show you the technique for these. So first off, with square roots, the big trick here is remember that the opposite of a square root is a square, or a second power. So to solve these, we're just going to square both sides. That's the big trick here. So I take the square root side, square root of 20 minus 8x, and I square it. And I take the x side, and I square it. And you're allowed to do this. You can square both sides of an equation. When you do this, the square and the square root are opposites, and they do cancel. So that doesn't change the numbers on the inside. It just gets rid of the square root and the square. So you just end up with a 20 minus 8x, now with no root. We couldn't really solve it before when there was a root, so we need a technique like this to get rid of the root. Now on a problem like this one, I do have an x squared. You will see a lot of quadratics pop up in this section. We're dealing with the root equations, these radical equations. So the trick here is to solve this radical. Usually, I shouldn't say usually, I'll always give you problems where you can solve them by factoring. And the way to do that by factoring, you have to get equal to 0. Since they like to keep my x squared as a plain x squared, I don't want a negative, I'm going to actually move these two numbers to the right side and leave the x squared where it is. I'm not going to move it over here because then it becomes negative. So I'm going to add the 8x across. I'm going to subtract the 20 across. So I can get rid of this stuff on this side because I'm trying to get this side equal to 0. So I get an expression, a quadratic, where it's equal to 0. So I have x squared plus 8x minus 20. There you go, quadratic equal to 0. Now I can just factor it. When I factor, since x squared at the front, plain x squared just makes it plain x's. That's why I like that plain x squared, because it makes the first part easy. Now I just got to think of what multiplies for negative 20 and adds for 8. So multiply for negative 20, add for 8. Sounds like 2 and 10, right? 2 and 10 multiply for 20, and if you subtract them, you can get 8. I'm just going to say 2 and 10. Since we want a positive 8, we're going to make that a positive 10 and a negative 2. So that's how we get that value. So again, anytime you have quadratic like this, get it equal 0, factor it, and I will give you ones in this section, or at least this section of the the homework and the quizzes and any problems like this on the test, you should just be able to factor them. I won't give you whether we have to use the formula if it starts with a radical like this. Okay, here I got 0 equals x minus 2, 0 equals x plus 10. I add 2 across, so I get x equals 2. Subtract 10 across, so I get x equals negative 10. Okay, that's it for solving these. So all you have to do is square both sides and then just solve the equations that's left. A lot of times the equation that's left will be a quadratic. That happens a lot with these. When you square both sides, you end up making a lot of quadratics. And when you do that, once you get that, you'll get your 2 answers. But there's a catch. Although squaring both sides is a valid way to get answers, it actually does sometimes give you what we call extraneous solutions. It's just a fancy math way of saying sometimes the answers you get are not valid. You have to go back and check them. You must check. And how do you check? Well, you go back before you ever squared anything. I like to go back to the original equation every time just to be safe. In that original equation, you plug in the number and see if it really does work. You're going to check one number at a time. So first we're going to check. We're going to check x equals 2 and see if it works. So I'm going to take this expression, this equation, and plug in 2 for both x's. So I get root 20 minus 8 times 2 equals 2. And see if it works. So 8 times 2 is 16, so this is root 20 minus 16 equals 2. 20 minus 16 is 4, so I get root 4 equals 2. And that's true, right? Square root of 4 is 2, so it works. So 2 is a valid solution. So we're good right there. Then we have to check the other one. So now we're going to check x equals negative 10. So the same square root, 20 minus 8, but now it's 8 times negative 10. And see if that equals negative 10. Well, 8 times 10 is 80, so this would be 80, and the negative negative makes it positive. So we end up with 20 plus 80 under the square root equals negative 10. And 20 plus 80 is 100. And square root of 100 is equal to negative 10. You say, well, does that work? Because square root of 100 is 10, and you should look at it and say, well, but it doesn't, because remember that this square root symbol only asks for the positive answer, and this is the negative answer. If you want a negative 10, you'd have to have a minus in front of here. So this actually does not work. It's not true. In fact, I knew it didn't work as soon as I wrote down this expression, this equation, because you can't take a square root and get a negative unless there's a negative in front of it. So right here, you already knew it wasn't going to work. In fact, negative 10 is not a valid solution. But you could hopefully see why squaring both sides make it look like it works. Because you take this expression where there's a negative 10 on this side and a root on this side, if you square both sides, it gets rid of the negative here. It makes it positive. It makes it positive 100. Like we kind of get towards the end, that's positive 100. If you square the side, you get a positive 100. So the squaring both sides kind of loses some negative information, and that's why it makes some answers look like they work when they really don't if you check them. So that's why you have to be really careful. If you square both sides, some answers work, some answers don't. It is possible to get 2 answers that do work. It's possible the answer, both answers don't work. So you have to always check all your answers. If you square both sides, if you have a radical equation like this, square root equation, and you square both sides, you have to go back and check your work. And it's something you should be really careful with. And I'll probably put the note about that on the test. If I have a problem like this, I'd say, check your solution. And so you want to make sure you do that. If you don't check your solution, then you'll lose points, because that's part of doing this problem, is go back and make sure that the answers are valid answers. Okay, let's try another one so we can kind of get this idea and keep going with it. Okay, so I have square root of x plus 10 plus 5 equals x plus 3. So I've got square root on this side. I want to square both sides, but before I do, notice that there's this extra plus 5 over here. If you try and square this side with 2 parts, you're going to end up having to actually do a FOIL problem. Remember that when there's 2 things and you multiply with the power, like a square, you can't just square both parts. It doesn't work with addition. You have to actually FOIL it out. So to make life easier, and really to make this problem possible, because if you don't do this, it really doesn't work, we actually need to get this root by itself first. The first thing we're going to do is isolate the root. You always want to get the root by itself first. So before I square both sides, I should subtract 5 across first to get rid of that 5. And so then I just have the root x plus 10 on this side, and on this side I have x minus 2. Once you have the root by itself, then square both sides. So you always want to get that root by itself before you square both sides. So once I get that by itself, now I can take and I can square this side and square this side. Here I'll have to put a parentheses there to square that side. Over here, you can see the square root and the square cancel. That's the whole point. Get rid of the square root by squaring. So just get x plus 10. Over here, this one ends up being a FOIL problem. I always get students who think you could just square the x, square the 2, and call it good. That doesn't work. Can't do it. You actually have to do x minus 2 times itself, x minus 2, and FOIL it out. So if you FOIL this out, you get x times x, you get x squared. You do outside, x times negative 2 is a negative 2x. Inside, negative 2x. Last is positive 4. You can see how you actually end up with 3 parts, because the middle part, these two combine, you get negative 4x. So this should become x squared minus 4x plus 4. So whenever you have something like that squared, you actually have to FOIL it. You can't just square both parts. It doesn't work. People try to do that all the time, and that's not how squares work. You can square both parts of multiplication, but you cannot square both parts of an addition or subtraction. It doesn't work. Okay, most of these, like I said, turn into a quadratic. You get an x squared in there. So to solve these, we'll get it equal to 0. So I'm going to subtract the x across, subtract the 10 across. That way I can get rid of this stuff. So I get 0 equals x squared minus 5x minus 6. So I got rid of that stuff equals 0. And then I'm going to factor this thing. Again, I'll give you ones that factor. I'm not going to give you a problem like this and make you use the formula as well. This problem, you'll definitely be able to factor. So this is x's, because x times x, 2 to x squared. And you can multiply for negative 3, add for 5. I think 2 and 3 should work, maybe? 2 times 3 is 6. Oh, but 1 has to be negative. And if I do 2 plus negative 3 or negative 2 plus 3, I have to get like 1, and 5. So I think I actually have to use 1 and 6. 1 times 6 is 6. To get a negative 5, let's make the bigger one negative. So that way when I add these, I get a negative 5, but when I multiply these, I get a negative 6. So that should be my answer. So here I multiply x times x is, or I'm not, why am I multiplying? I just factored it. Sorry. Got distracted there thinking. Alright, so here I take both parts equal to 0, so I get 0 equals x plus 1, 0 equals x minus 6. Subtract 1 across, so we get x equals negative 1. Add 6 across, so we get x equals 6. And there's our 2 solutions. But just like on the previous one, we must check. Gotta go back and make sure these actually work. It's always possible that you get answers that don't work. They could both fail, so you have to check both. So first off, let's check and see if x equals negative 1, what happens. So if I do this equation, I have square root of negative 1 plus 10 plus 5 equals negative 1 plus 3. Then I have negative 1 plus 10, which is 9. So I square root of 9 plus 5. Negative 1 plus 3 gives me 2, so it should be 2. Well, square root of 9 is 3, and 3 plus 5 is not equal to 2, right? 3 plus 5 is 8. So that doesn't work, which means that this negative 1 is not actually the odd answer. Now, I know both times so far the negative number hasn't worked. That doesn't always hold, so don't assume that. I always get students to say, is it just because they're negative? No. Sometimes the positive answer can be the false answer. So you can't make that assumption. So you always have to check both. So don't just assume just because it's negative it doesn't work. Sometimes the negative one works and the positive doesn't, so you have to check both. Let's try the other one. Let's try the x equals 6 and see if it works. So I get square root of 6 plus 10 plus 5 equals 6 plus 3. Square root of 6 plus 10, well that's just square root of 16 plus 5. And 6 plus 3, that's going to give us 9. 16 square root of that is 4, plus 5 would be 9. And so it does check out. So 6 is a valid solution. And again, it's not always going to be there's one answer that works and one doesn't. It's definitely possible to have one answer that works, have both answers not work or both answers work. This can happen as well, but so when you're checking these, you do need to check both answers. Every answer you get by squaring both sides must be checked just to see if it really is valid. Okay. I want to show you this one. This one you'll see in the homework. I think there's just 1 or 2 problems with like this in the homework. I will not put one like this on the exam. It's just too time consuming. This one you'll see when we do it has a lot of steps. It's easy to make a little mistake here or there and have a hard time with the problem. So I'm not going to put this on the exam. It might show up in the homework, maybe in the quiz. It definitely shows up in the homework. It might show up in the quiz. But don't freak out too much about this one. The problem that we saw just previously, that's going to be more likely like what you'd see on an exam question, something like this, where you have to get the number off to the other side and then square both sides. That's probably something similar, more like what you would see on the exam. This is more of a, it's good to know these exist, maybe see one and do one, but I'm not going to test you over it. So don't worry about this one on the test. It will not show up on the test. Okay, so let's try it. So we're going to take this thing. First thing is, just like before, we need to isolate the root. The problem is there's two roots, and you can't isolate both because we also have this 3. So we're actually just going to isolate a root. So if we can get one of them by itself, that works good enough to solve this problem for now. So what we'll do is, because the square root of 2x plus 7 is positive, we'll leave this here. Let's take this negative root and move it to the other side. So we're going to add to get rid of it. And if we do that, of course, we have to do that to both sides. That's how we ended up with that on the other side. So we'll add, get rid of this one, so we can get the root 2x plus 7 by itself equals 3 plus root x minus 5. Okay, so now if you hit one root by itself, once you get a single root by itself, then we'll square both sides. Since there's two things on this side, we do have to use parentheses, and we do have to FOIL on this side. That's where you got to be careful, because when you have two parts, you have to FOIL. This side, thankfully, just cancels. The root and the 2 cancel, so we just end up with 2x plus 7. Over here, we FOIL. So we're going to multiply this times itself. So we're going to have like 3's on both fronts, so the fronts will be 3. So 3 times 3 gives me 9. Outside, we're going to have 3 times like a root x minus 5. So it would be plus 3 root x minus 5. Inside would be root x minus 5 times a 3, because you can imagine this having another one next to it. So we'd have another 3 x minus 5. And then the last is going to be root x minus 5 times itself. Well, if you multiply something times itself, the same thing as squaring it. So it's going to be a root x minus 5 squared. So that's what you get if you FOIL that with itself. So FOIL with itself. If you need to see more of that, you can always take this and write it down twice, and then you can maybe hopefully see what that first, outer, inner, last is. But it should give you this when you multiply. The middle two terms here do match, so we can combine those, right? They have the same root on them. So they combine, so we have 3 of these plus 3 more, so you end up with 6 of these root x minus 5s of the 9 in the front. Here on the back, notice that the root and the square cancel, so we end up with just x minus 5. Okay, so at this point, you notice that we went from having 2 roots to having just 1 root. And so that's why, even though we didn't finish this, we don't have a final answer or anything, squaring both sides is still valid. If you can get a root by itself, you can get rid of at least one of the roots and get to the point where you have less roots. So in this case, it works to do this. Now we just got to do one more step where we get this root by itself again, do another isolate the root, and then square both sides again. So that's the big difference in this problem is end up doing that, squaring both sides twice, once for each root. Okay, so here I want to get this by itself, so I'm going to go ahead and do some things like combine. I'm going to subtract 9 across, get rid of that 9. Subtract x across, get rid of that x. I'm going to add 5 across, so get rid of that 5. So I'm just trying to get rid of all this other stuff. Oops, I put that 5 in the wrong spot. It's supposed to be over here. This is the same side. That was a mistake. Okay, so I get 2x minus x is x. 7 minus 9 is a negative 2, but then I add 5, so I get positive 3. So, doing both the subtracting 9 across and the adding 5 across. Over here I still have the 6 and the root x minus 5. But that's it. I'm not quite to the root by itself. I still have the 6 here, so I am going to get rid of this. Since this is multiplied, to get rid of it, I'm going to divide both sides by 6. So to get rid of that multiplication, I am going to divide. So now this side is x plus 3 over 6 equals root x minus 5. Up here now, I have the root by itself, so I'm ready to square both sides again. So I'm going to take that and square it, take that and square it. Square root, the square cancel, right? That's the whole point, is to get that x minus 5 by itself. Over here, remember that the fraction, you can square the top and the bottom separately, so I can square the top, x plus 3, I'll do that. But I can also just square the bottom by itself, so 6 squared is going to be 36. To make my life a little bit easier, I'm going to go ahead and multiply by 36 to get rid of this fraction. Now that I got rid of my root, I'm going to go ahead and get the 36 back over and multiply it to both sides. So now I don't have to worry about having the root by itself anymore. And over here, I'm going to do x plus 3 squared. If you square that, that means multiply it times itself. You do get x squared plus 6x plus 9. So if you take this and you FOIL it with itself, that's what you'd get. Don't just do x squared, 3 squared. Remember, you have to take this thing x plus 3 times x plus 3. And when you multiply it all out and simplify, you end up with this expression. Over here, I'm going to distribute 36 to both parts. So we get 36x minus, what is that, 150 plus 30 is 180. We're getting there, we're not there yet. We want to solve this, so we want to get the quadratic all on one side. So I'm going to subtract 36x from both sides. I'm going to add 180 to both sides. So got rid of this, got rid of that. So I end up with x squared minus 30x plus 189 equals 0. So I got to stop and think, what multiplies to give you 189? Does anybody know what multiplies to give you 189? So I think 189 divided by 3. Yeah, 3 and 63, but that's not going to help us. If I take 189 divided by 6, nope, 189 divided by 13. Oh, 21. Divided by 7. Or nope, that doesn't work either. 189 divided by 9. There we go. Okay. This is one of those ones that's so bad I had to even think about it and stop thinking about it. So in order to get two numbers that multiply for 189 and add for 30, eventually I figured out that 189 divides by 9, and 9 times 21 is going to give you 189. And 9 times 21 is great because it adds 9 plus 21 adds for 30. So that would be my pair of numbers. Now I wouldn't, like I said, give you one this bad on the test. First off, I wouldn't give you a problem like this on the test, but the factoring here is kind of messy too. I'm not usually that mean on the exam. Okay, so this would be minus 21 and x minus 9. It's got to be both negatives because they have to multiply for a positive and add for a negative, so they can both be negative. So here my two answers would be x equals 21 and 9. But even after all that work, because we squared both sides, we still have to go back and check. It's still possible if these two answers aren't any good. So we still have to go and check our solutions. So first off, let's check the 21 solution. So let's see if x is 21, what happens. So I'm going to take this expression, and for every x, I'm going to plug in 21. So I get root 2 times 21 plus 7 minus root 21 minus 5, and see if that equals 3. So 2 times 21 is 42, so we get 42 plus 7. 21 minus 5 is 16, so root 16. 42 plus 7 is 49, so root 49. Root 16 is 4, equals 3. Root 49 is 7, minus 4 is 3. And 7 minus 4 does work and give you 3. So 21 is a valid solution. So far, so good. 21 works. Now I got to check the other one. Let's check x equals 9. So again, I'm plugging it back in the original equation. So I get root 2 times 9 plus 7 minus root 9 minus 5, and see if that gives me 3. 2 times 9 is 18 plus 7. 9 minus 5 is 4. 3. 18 plus 7 is 25. Root 25 minus 4. Root 4 is 2. That gives me 3. And root 25 is 5. So I got 5 minus 2 equals 3. And it does. And this is one of those examples where both answers work. If you didn't check this on the homework, you wouldn't even notice because they both work. But like I said, sometimes one works and one doesn't. Sometimes they both fail. Sometimes they both work. You need to check them every time just to make sure. Does it really work? And so we checked them and found that both of these work. They're both valid solutions. So we can keep both answers. Okay. That's the primary thing we're going to see with the roots. I do have one more page just to show you that not all roots are square roots. Sometimes you might solve an equation with another kind of root, like a cube root. Now, hopefully you can guess what we're going to do. With square roots, we squared both sides. With cube roots, we cube both sides. And that just means do the third power. So remember, a cube root is like a square root. It just, instead of saying something times itself, just two of them, it's saying something times itself 3 times. So the 3 tells us to get rid of that. To undo it, the opposite is the third power. So here we cube both sides. So just like we did with square roots, only instead of doing a second root, doing a second power, we do a third power. We take that cube root, that third root, and we cube it. because that's its opposite. So it's not too different, right? Fairly similar to what we've been doing. And this expands. This could continue on. So if you have a fourth root, it has a 4 there instead of a 3, you take the fourth power of both sides. If you have a fifth root, you do the fifth power of both sides, so on and so forth. Okay, so cube root, cube both sides. It's the opposite of that cube root. So 2x minus 5 equals 5 cubed, which 5 times 5 is 25 times 5 gives you 125. So that's what you get when you cube a 5. You can do that in your calculator. If you're not sure about doing cubes on paper or in your head, the math button does have a cube as the third option. So that the cubing, third power there. So you can do that. Or you could do just, 5 to the power of 3 using the power button right here. Either way to get 125. Okay. So 2x minus 5 equals 125. I'm going to add 5 across because now I'm just solving this equation. For x, this one didn't even turn to a squaring because we were doing cubes that end up just with a regular x. I just have to get x by itself. 125 plus 5 is 130. 5 by 2 on both sides. Get the 2. So we get x equals, what's that, 65? Now the nice thing about cubes is not only does it work very similar, these ones you don't have to check. So we're not required to check. You're welcome to. If you want to go back and make sure it works, you can, but you don't have to. Because when you cube both sides, you'll never have that false stuff happen. With squares, with even powers, remember they mess up the negatives, but odd powers, like cubes, they don't mess up the negatives. They keep them. Negative 1 to the third is still negative 1, versus like negative 1 squared is positive 1. So an odd power or odd root doesn't make you check. You don't have to. You can just call the answer good when you get to here. If you want to, you could go back and check it. You put 65 in here. 2 times 65 is 130. Minus 5 is 125, and the cube root of 125 is 5. It does work. You can go back and check it. We don't have to. So be ready for some cube root problems. Last thing here is this one looks way different because they have this 1/3 power. This is your friendly reminder that a 1/3 power is the exact same thing as a root. Remember, a to the 1/3, so any number to the 1/3 is the same thing as the 1/3 root, or the third root of a. So they'll sometimes give you problems like this, and you look and go, oh, what do I do with that? Well, it's the same problem. You just cube both sides. So I take this x to the 1/3, and I cube it, and I take this -4, and I cube that. Because it's still the same thing as a cube root. Notice here that since this is a power to another power, remember the rule is that we use the power rule where we multiply the powers. Well, what's 1/3 times 3? Well, 1/3 of 3 is 1, so this becomes x to the first, or just x. So if you ever have fraction power, you just multiply by whatever's going to get rid of the fraction. So 1/3 times 3 gets rid of the fraction. Just like we saw up here, cube root and the cube canceled. The 1/3 and the 3 we're going to basically cancel. Over here I get -4 to the third. Well, -4 times -4 is positive 16 times a -4 gives us a -64. So if you don't trust me, you can do 4 to the third, you get 64, and 3 negatives make a positive, or make a negative, because 2 of them cancel out and the third one's left over. So that's all that is for that one. So it looks crazy, but you still just cube both sides. If it was a 1/4 power, you do the 4th power both sides. If it was 1/5 power, you do the 5th power both sides. So something they throw in there because it looks way different, but remember that 1/3 power is the same as cube root. In fact, if you wanted to, you could rewrite this as cube root of x, and then just solve it using the cube of both sides. I didn't even bother rewriting it because I know that the third power and the 1/3 would cancel, so I left it like that. So that's it. Okay, so we solved those rational equations with x's and logarithmic fractions, and we solved radical equations that have roots in them. Next section, we will solve another type of equation. So we're doing a lot of equation solving here for now, but we'll see you then.